Today we'll take a look at direction fields and Euler's method. We'll discuss how to sketch a direction field for a differential equation. We'll sort of interpret those a little bit. And we'll also talk about this Euler's method to estimate function values using a differential equation. There are ways to solve some differential equations, but not all of them. In fact, most can't be solved explicitly using algebraic methods. So even if that's true, though, we can use approximations, as we've seen in other cases. We can approximate a function solution based on what we know about derivatives. We'll also use this idea of a direction field or a slope field to visualize what a differential equation might mean, and we'll sketch out solutions based on those direction fields or slope fields with a specific initial condition. So take a look at this one. This is a pretty straightforward one. We've got the differential equation y prime equals x plus y. So the derivative, or the slope, is equal to simply the x-coordinate plus the y-coordinate. You might be able to see that by looking at these line segments that are sketched out on the direction field. Take a look at the top part. Right? If you choose any particular coordinate pair, like 0, 0, then you'll notice that the slope should match what's described in this differential equation. At the point 0, 0, the slope is 0. At the point 1, 0, the slope should be 1 plus 0, which is equal to 1. And those trends should continue, right? As x gets larger, the slope increases. As y gets larger, the slope increases as well, both on a linear scale. So that you can hopefully sort of start to look at those series of line segments there that represent slopes, and you'll see sort of how that works, right? So again, each line segment represents the slope of whatever your solution function is for that differential equation at that given point. So what we can also do is, if you notice on the bottom graph, we can choose an initial condition, like the point 0, 1, and generate the specific solution for the differential equation based on that. Sort of just sketching out a curve, sketching out a function that follows those slope fields, the direction fields that are provided. So if we follow along the slope, we know that the function is going to increase as we go to the right of the starting point. And we know that the function is going to start out decreasing as we go to the left. But we can see there's sort of a line of constant slope there of -1, which this is actually going to approach as we go further to the left. So we'll kind of just sort of try to sketch out a function that follows along that smooth curve there. Again, this sort of, the curve represents this, we would say that it's a particular solution that goes through the point 0, 1, or that satisfies y of 0 equals 1. This sketch is another example, a different piece of software generated this one, so there are arrows instead of line segments. But you can imagine this one, also there's not a good scale indicated on the xy plane here, but suppose that this is your slope field or your direction field for y prime of t equals -0.5 times t minus 75. Notice there are two red curves drawn in there. Those are two different particular solutions with different initial conditions. And also notice that there's a horizontal line going on as you cut sort of halfway between those two. Right? We can see that this slope field has a place where no matter what x we choose, for that fixed y value, there is a slope of 0. So we've got two curves that are indicated there, and they represent different initial conditions, which the curves look different, right? They look like they have the same rough shape, but one is concave up and decreasing, the other is concave down and increasing. That comes from the idea of the initial condition, right? So if we have an initial condition that's above 75 when t or x equals 0, then we end up with a function like the top one. We get a function like the one below if our initial condition is less than 75. This could be a result of setting up a differential equation to model a heating or cooling. You might look up Newton's law of heating and cooling, where the ambient temperature is 75 degrees. Let's take a look at a direction field. You won't be asked to do this much, if at all, but picture how you might sketch out a direction field for example, this function, this differential equation, y prime equals x squared plus y squared minus 1. In order to sketch a direction field, all you would need to do is simply determine what the slope would be at a series of points. Again, don't do this, it's pretty painstaking, but take a look at what I've done and sort of compare, make sure it makes sense. If you calculate x squared plus y squared minus 1 for a variety of coordinate pairs, I oriented them sort of like they would look on a coordinate plane, you should be able to calculate slopes like this. Remember, this y prime is like dy dx, that represents the slope. And so in order to sketch that direction field out, notice we would end up with a slope of -1 at the origin. So we'd draw a line segment that has a slope of -1 near the origin. And then continuing to trace out more in nearby points, you can sort of see a trend like this start to occur. This is a really neat example too. I like thinking about this one. Take a look at these 4 different differential equations, and using some symmetry, see if you can identify which of those 4 differential equations matches with each of the provided A, B, C, D direction fields. Again, look for places where the slope would be 0. Look for places where the slope might be undefined. Look for general patterns of symmetry that you might notice, and see if you can identify those. For our solution, once you've tried that a bit, right, number 1 matches with part D. And that might actually make sense because this looks like a linear function, 1/2 x, and so we know its solution should be a parabola shape, which looks kind of like this. We see that part 2 should match with the graph for B. And again, that might make sense because this is like a 1/2 times y prime equals y, which means that we should have some e to the x shape happening here, some exponential function. So 2 should match with B. Number 3, differential equation for number 3 should match up with the graph for A. And once again, that kind of might make sense. We see this x squared plus y squared. There's some symmetry here. And also we notice that this is sort of a circular shape, so we can kind of see a circular trend happening in there. That would not be careful here, that would not be the graph of one of your particular solutions. That does not follow along the slope field. In fact, it should do something like this instead. But we do see that circular trend, which might come from that x squared plus y squared part. And lastly, notice for number 4, that one should match up with C. And that vertical slope is the thing to look for there. Unlike the others, there are places where your denominator here could be 0. That would be when x equals 0. And so notice along that line x equals 0, we do end up with a vertical slope for our slope field. And that's the only one in this set that has that sort of property. Let's take a look at one more idea. This is Euler's method. Not necessarily pertaining to slope fields, but definitely working with numerical approximations for differential equations and their solutions. So this has to do with the idea of a linear approximation, which you've probably done before at some point. A basic strategy that sort of defines Euler's method sounds like this. Right, we start with a differential equation, which is like an equation that gives us a slope. Kind of like we did when we generated a slope field, we'll use that differential equation to come up with the slope near a given point. We will apply that slope in a very close area to that point. For some step size, we'll call it h, or sometimes people use delta x. And we'll essentially apply that slope in order to calculate a close by point that might be on the function relative using that same slope. That's what we'd call a linear approximation of the point, and that's where that function will come in. Essentially, we're calculating a new x-coordinate by taking an existing x-coordinate and adding some step size to it. And we're calculating the new y-coordinate in almost the same way. But what we're doing is we're taking that y-coordinate, the previous y-coordinate, and multiplying that step size. There should be a prime symbol there. That's the first derivative, right? We're multiplying the step size by the slope. Again, this is a function of x and y, right? Your differential equation may include x's and y's in it. So we're multiplying by the slope at that point times the step size to give us the change in y that we expect. So we determine our slope at our new point using that differential equation, as we just mentioned, and then we apply that slope with the same step size to continue on and generate more and more points. That series of points represents an approximation of a solution. It gives us what we think a function might look like that is a solution to a differential equation. And we'll repeat that as many times as we need to. So let's take a look at one example of how to do that. We'll use a step size of 1/2, and we'll try to approximate y of 1.5. So we'll try to approximate the function's value at 1.5 given a differential equation here. Y prime equals 3x squared. That's, I think, the very first one we looked at. Y prime equals 3x squared. We know that that should fit the family of x cubed plus c. So we could even solve for c with that given initial condition, y of 0 equals 5. And so you know at that point that you can decide exactly what particular solution there should be here. So maybe do that on your own and compare that to what we get with this approximation. But starting with the initial point x equals 0, we're going to approximate the value when x equals 1.5 using this linear approximation. This table is a good way to sort of organize some of that info, and we'll kind of step through it. I made a column for n here. You don't need to do that. That just helps me keep track of sort of where we are. Right? For x of n, our initial point is this one, the point 0, 5. I've filled out the rest of those x coordinates by adding the step size each time. Right? We're going to need 3 iterations here because our step size is 1/2, and we want to approximate 1.5. So we'll have to step up by 1/2 3 times. And then to get those preceding y, or the succeeding y values, we're going to need to plug in and actually use our linear approximations. Right? We'll take the 5 value that was our first y coordinate. We'll add the step size multiplied by the derivative at that original point. So we'll plug in 0 and 5 into the differential equation. In this case, that just means plugging in 0 for x. And so we end up with a slope of 0 there, which means that our next approximation point is still going to have a height of 5. And that's okay. That 5 comes down and becomes this next y value. Iterate that twice more. Right? We'll use 5 for our starting y value again. We include the step size again. We plug in, and this time it's not 0, right? We plug in the x coordinate into our differential equation, and so we get 3 times 1/2 squared. The total there, including the initial 5, becomes 5.375, and so that moves into our next y coordinate. We'll use the point 1, 5.375 as another approximating point for our function. You can iterate that one more time, and you'll get the y value of 6.875. I recommend that you take a look at the graph of x cubed plus, in this case, if you were to plug in x equals 0, you should end up with a 5 for your constant there. So I recommend graphing x cubed plus 5 and comparing these two things. One more example that we'll take a look at. This was a differential equation that looks slightly more complicated. Y prime equals x cubed plus x squared. And we're starting with an initial condition, y of 1 equals -2. So we've got the point 1, -2 to start with. And our goal is to estimate y of 2 using a step size of 0.1. Notice we're trying to cover an x distance of 1 using a step size of 1/10, which means we're going to need 10 iterations. I highly recommend using Excel or something, and I'll share a file that you can use for this problem in Excel so that you can see what that might look like. But I recommend using technology to save some time in this process. You could do the same thing 10 times algebraically, or use technology to make this a little bit faster, but we're essentially doing the same thing. Right? We're taking an existing y value, we're multiplying the step size by the slope at that point, and then we're using the result as our next y value, and we'll keep iterating that way. Once again, I'll include a file that you can use for this particular problem to see how to do that pretty quickly with Excel, but you should be able to, using this Euler's method, come up with some function value approximations, even if you don't know what the function itself would be.